In the last video, we discussed how to differentiate a curve. In this video, we will look at some examples. The first example is perhaps the most familiar example of a curve, namely the curve f from R to R2 defined as f of t is equal to cos t comma sin t. As you know, the image of this function is the familiar circle. This is because cos square t plus sin square t is always equal to 1. Therefore, the point cos t comma sin t is always at a distance 1 from origin. Notice, however, that this function is not 1, and it loops around the circle many times. At 0, f of 0 is equal to 1, 0, and as t increases, the point goes around the circle. As t becomes 2 pi, it reaches back at 1, 0. Again, it goes another loop as t varies from 2 pi to 4 pi and so on. So it wounds around the circle infinitely many times. Let us now look at the derivative of this function f dash of t. We saw earlier that the derivative of such a function is given by the derivative of its components. That means we have to take the derivative of cos t, which is equal to minus sin t, and the derivative of sin t, which is equal to cos t. So derivative of f at t is equal to minus sin t comma cos t. Recall that f of 0 was equal to 1, 0, and from this computation we see that f dash at 0 is equal to 0, 1. That is, the tangent at the point 1, 0 is this vector 0, 1. Of course, notice that I have plotted the vector 0, 1 at the point 1, 0 instead of plotting it at the origin. But once we do that, it matches with our intuition that the tangent to a circle is a line that's perpendicular to the radius. So it matches very well with our intuition. Similarly, you can also notice that f of pi by 2 is equal to 0, 1. And the derivative at pi by 2 is equal to minus 1, 0. In other words, we are saying that the derivative at the point 0, 1 looks like this. Once again, this matches with the intuition we have about tangents to circle. Similarly, we can show that the tangents at all points are as we would have expected it to be. Of course, I am not going to compute the tangent at all points, and I leave it to you as an exercise. Let us now look at another example. This time we are considering a function f from R to R2 defined as f of t is equal to 1 minus 3t square, 3t minus t cube. Once again, as the component functions are polynomials, we know that this function can be differentiated. The derivative of the function will be given by the derivatives of the component functions, which is minus 6t, 3 minus 3t square. Thus, this function is differentiable at all points. However, you will be in for a surprise when you look at the graph of this function. The graph of this function roughly looks as follows. That is, the image intersects itself at the point minus 8, 0. More precisely, you can notice that f of root 3 and f of minus root 3 are both equal to minus 8, 0. Therefore, it may appear that it is difficult to define the tangent at the point minus 8, 0 because it's not clear whether we should consider this line or this line. But recall that our interest was not in the image of the function, but rather the path traced by f of t as t varies. As t varies, f of t traces a path as follows. More precisely, as t approaches minus root 3, we approach minus 8 comma 0 this way and then continue along and reach minus 8 comma 0 again at t is equal to root 3. Further notice that the derivative of a function at a point depends only on the values near that point. So near minus root 3, the image of the function looks something like this, and therefore the tangent will be a straight line like this. Similarly, near root 3, the image of the function looks something like this, and therefore the tangent looks something like this. And this matches with what we get when we compute the derivative at minus root 3 and plus root 3. Notice that f dash at minus root 3 is equal to 6 root 3 comma minus 6, and f dash at root 3 is equal to minus 6 root 3 comma minus 6. That is, as expected, the derivative at minus root 3 has a positive x component but negative y component. On the other hand, the derivative at plus root 3 will have both its components, x component and y component, negative. There is one more way to resolve this conflict at minus 8 comma 0. That is to look at the graph of this function rather than the image of this function. Notice that the graph of this function does not intersect itself, and therefore we can uniquely determine a tangent at all points. However, there is a slight issue. This tangent line that we get is a line in R3 instead of R2. But for us, the derivative was a vector in R2, and therefore what this derivative mean in terms of this tangent line is something that we need to really think about. I encourage you to use GeoGebra or similar softwares to explore this avenue, but I am not going to go much deeper into this aspect. Now we will look at another example which will further convince you that even though a curve is differentiable, its image need not look nice at all. This time we will be looking at the curve f from R to R2 defined as f of t is equal to t square comma t cube. If you plot the image of this function, you will notice that the image has a sharp point at origin. However, the function itself is differentiable as both its components are polynomials, and it's easy to compute the derivative. Namely, it is equal to 2t comma 3t square. Thus, even though a curve is differentiable, its image can have a sharp point. The intuition here is that as we are approaching origin, we are slowing down so much that we are almost at a halt when we reach origin, and then we pick up speed again and go in the other direction. Because we sufficiently reduce the speed, we do not feel a jerk as we cross the origin. And this idea is captured by the derivative. Notice that f of t is equal to the origin if and only if t is equal to 0. And f dash of t is equal to 0, 0, the origin. In other words, we do not have any velocity at t is equal to 0. So we are completely at a halt when we are at origin. Once again, plotting the graph of this function might give you some more insight into what is really going on. So please use GeoGebra or any other software to plot the graph of this curve.